Welcome to the pre-conference statistics session of the 34th Annual Scientific Meeting of the Eastern Society for Pediatric Research, or ESPR, and the very first Annual Eastern Medical Research Conference with our new partners, the American Federation for Medical Research, or AFMR. This new partnership is very exciting as we learn about colleagues whose work we might not be exposed to, and our organizations work together to support mentor trainees and early career researchers. I'm Heather Brumberg, president of ESPR, and I'm sending my well wishes to everyone today. The mission of the Eastern Society for Pediatric Research is to foster the development of multidisciplinary careers, promoting pediatric research. Our goal is to provide investigators, especially trainees and junior faculty members of all races, ethnicities, religions, and sexual orientations, gender identities, and abilities, with an opportunity to meet and present their research for critical review and feedback. It is important to note that our focus is on pediatric research, not just research by pediatricians, as exemplified by many of our conference presenters. We are disappointed that we could not host an in-person meeting, but we hope that the pre-conference sessions, together with all of our oral platform and oral poster sessions, will give us a chance to showcase the amazing science being conducted despite the pandemic and all of its associated challenges. All the abstracts presented can be viewed through the conference website. ESPR has many opportunities for members to get involved, from committees to abstract reviews to moderating sessions. Please, to learn more about these opportunities, email easternspr@gmail.com. That's easternspr@gmail.com. And if you're not yet a member, joining is just a click away. Go to the easternspr.org site and go to the membership tab. I would like to thank our sponsors, especially Me Johnson Reckitt, who is sponsoring this session, and a special thanks to Dr. Jayshree Nair, our planning committee chair, who has spearheaded this virtual meeting format and who will be introducing our speaker, Dr. Spancic. Dr. Nair.
Hi, good afternoon, everyone. Thank you, Heather. And it is my absolute pleasure to welcome you to this workshop on common statistical errors, and to introduce Dr. John Zupancic, who's an associate professor of pediatrics at Harvard Medical School and associate chief of neonatology at Beth Israel Deaconess Medical Center. Dr. Zupancic's research and consulting work is known to many of us, and it seeks to improve the efficiency with which scarce resources are used in improving the health of children, particularly newborns. He has focused on performing and improving the validity of economic evaluations alongside neonatal clinical trials, and on the use of computer modeling to determine best practices when evidence is currently lacking. He's also involved in various epidemiological and health services investigations, including the Neonatology Canon Project, a large-scale systematic review of all randomized controlled trials in neonatology over a 24-year period. Dr. Zupancic is a past chair of the American Academy of Pediatrics section on neonatal perinatal medicine and has received several awards, too many to mention here, for teaching and mentorship, both at his institution and nationally. He was also the recipient of the Massachusetts Medical Society's Henry Ingersoll Bowditch Award for Excellence in Public Health in 2020. And as some of my junior faculty remind me, an excellent speaker at the Neo Review board course, which just concluded. A few housekeeping rules for this session. Please keep your questions until the Q&A session and enter them into the Q&A tab on your screen. You should also be able to see a raise your hand tab on your screen. And if time permits, we would love to have you ask your question live. Questions can also be asked directly before or after the session on the Attendify pre-conference meeting page, and we'll pass it on to Dr. Zupancic. So again, thank you for being here today. And with that, welcome, Dr. Zupancic. I'm going to let you take over.
Thank you so much, Drs. Nair and Brumberg. It's so great to be here. I'm so sad we can't be there in person. It is great to be able to do this, that we have the technology to still connect. And so thank you for having me. I was saying at the start of this, actually, I'll just share my screen before we get going. There we go. Are you able to see that? Terrific. So I was saying to Drs. Brumberg and Nair at the start of this, that it's actually a little daunting to talk about statistics with particularly when you can't see the audience, but even at the best of times, it's a little daunting because, you know, unlike the case when maybe in medicine where there's a certain baseline level of knowledge that you can or experience that you can assume, with statistics, the you know, the people who are in a room together are very likely to have very heterogeneous exposure to either coursework or working on these problems. So that's you know, one issue. And the second issue is that comes up is the idea that when, you know, for those of us who have taken Stats 101 as part of our pre-med work, for example, or college work, often that knowledge lasts for somewhere around 8 or 9 days, I think, after your final exam, and then, you know, you have to go through this process of iteratively re-exposing yourself to it and relearning it. And then, you know, I think the latter, you don't have to feel bad about that. That's what we do, probably every single one of us, other than those of you who are geneticists, probably do it with the Krebs cycle, right? You have to go back and re-expose yourself. So those two issues, heterogeneous, you know, audience in the room, and this need to re-up on the fundamentals, kind of guides how we're going to take today. I think that what we should do is basically to do what all of us do on rounds, you know, at the bedside, where there might be somebody who's a medical student and somebody who's in residency and a fellow who knows more than you do, and you know, what we're going to try to do is to give a little bit of everything to everyone, and hopefully in the questions and chat we can tweak that even further. So the structure that I thought about that might be useful to do that is as follows. First, we're going to, for each section, generally, we're going to ask 1 or 2 or 3 framing questions that will kind of help us to see where everybody is, and also force you maybe to sit back and actually do something kind of active rather than assuming that the answer is right at the front of mind. Then after that question, I'm going to basically give some Stats 101 reminders, and I don't want, like I said, I'm not going to apologize for doing that, because the 101 part of this, because I have to go and look this stuff up constantly. Every time you mentioned the specialty review conference, Dr. Nair, and every time I do that, I go back and look up, you know, nuances about the p-value, for example. So I hope you won't be offended if some of this seems very, you know, some of that part of it seems a little bit basic, but then we'll gradually build on that. And I think the important thing is that a lot of the errors that we're going to run into in statistics actually have to do with a misunderstanding or a mislearning that we all had early on, or a misremembering of the potential errors. That's the sort of focus of this. And so at that, you know, understanding the fundamentals and understanding the errors is going to be important. And then for each of those issues, we'll talk about what the potential fixes are, and so you'll have a set of a dozen pages or so of stuff to avoid, and how to fix them when they happen. And then I guess the other important issue here, again, just like on rounds, is to make sure that there's an opportunity for all of you to ask questions. So please do that. You heard the couple of ways that you can do that. And if in the case that we don't get to some of your questions, or if they seem to be very, very specific, you know, I'm doing this project, I wonder if I can have a little consult, I'm always happy to do that offline. Okay, so let's just jump into the first question, and those of you who were at specialty review last week know this one. Taylor, are you able to bring up the poll for this? There we go. So the first question is in 4 parts. What type of data do each of the following measurements represent? So the first is biological sex. If you could just answer, does everybody, is it obvious how to answer that question? There we go. They're starting to come in. Okay. So I think you're actually able to scroll down and see the other questions, but we'll just go through those. So the second question is number of blood cultures, and you're going to choose categorical, ordinal, integer, or continuous. The third is the tumor staging for Wilms, which tumor. And the fourth is weight in grams. I'm a neonatologist, by the way, so I hopefully will scatter in patients who do not have their weight in grams, but apologies if. Okay, so let's just end that one. And what we see is that for sex, 100% of you answered, oh, here, I can share these results. There we go. 100% of you answered categorical for sex. For the number of blood cultures, it is fairly evenly split between integer and a couple of other options. Wilms tumor, about 2/3 of you said ordinal, and for weight, about 80% said continuous. So, thank you, Taylor. Okay, so just, this is one of those fundamental things that's really important to get right, because it's going to drive almost everything else we talk about today. So when we think about types of data, there are three dimensions, I guess, for lack of a better word, to describing them. The first is order. So is there any hierarchy? Does one come before another, either in terms of importance or in terms of impact or in terms of timing? Categorical outcomes, for example, have no order to them. We have male or female in the example that we had. Whereas obviously a weight is either higher or lower. There's some element of order there. Magnitude is the second thing. So is there an order to it? And ordinal is an example of a sorry, magnitude means that between one level and another level of the data, you have an equal space, essentially. So integer is an example of something that not only has order to it, but also has magnitude in the sense that 5 blood cultures is more than 4, and that's more than 3, for example. And then the third dimension is fairly straightforward, and that is decimal. Can you fractionate it? So obviously you can't fractionate a chest x-ray or a blood culture, but you can fractionate weight and apply a decimal to it. Okay, so that gives us the responses that most of you got. Categorical, or sex is a categorical variable. Number of cultures, of blood cultures, is integer. The Wilms tumor stage, I had ROP stage on a previous slide, is ordinal, since the staging increases in terms of impact, and weight is continuous. Okay, question 2 is this one, and it's in this diagram, which is a frequency distribution. What descriptive statistics do A, B, and C represent? Okay. And in the interest of moving things along, I'm going to end the poll each time when we get to about 2/3 of you responding. Just, but so I apologize if anyone has been left out. So for this diagram, we see that about 50% of you said mode, median, and mean, and the other 50% were fairly well distributed. Okay, well, as I said, that was an example of essentially a frequency distribution or frequency histogram, and that is something that you're going to see quite a lot of today, but also ubiquitously as you think about data. Basically, it is a classic graph where you put whatever it is that you're interested on the x-axis, and on the y-axis there's some measure of frequency. And then we can decide, once we've plotted, we can decide how to describe that. Oh, this just came back up again. Not sure why. We can describe how to describe that. So there are a number of descriptions. The first focus is on thinking about central tendency of a frequency distribution like this. The mean, as we all know, is calculated by taking all of the values, summing them up, and dividing by the n. At least that's one form of mean. The median is the value at which 50% of the values are greater and 50% are smaller. And the mode is the easy one because it's just the most common value. It's the highest frequency for across any of the x-axis. Now, these are relevant because they are differentially affected by outliers. So on this graph, what we see is that there's kind of a tail to the distribution out towards the right. We say that this is a right skewed graph. And the central marker is dragged out to a different extent based on which one we use. So a mean, you can imagine, supposing you had 5 values and 4 of them were 7 and 1 was 3 million, you could imagine that the mean would be really affected prominently by that outlier. It would be, the mean is pulled the most towards where the outlier is. And I actually think about just pulling on that string on the right. The median, though, in that case, wouldn't be affected that much at all, right? You'd have 4 sevens and a 2 million, and the median would stay more or less where it was. And similarly, the mode in that case would still be 7. It would be not affected at all. So that's really important because whether something is a symmetrical distribution or whether it's pulled over to one side, where the center of it is and what the center is, will help us to decide which tests we're going to use later on. Now, it can actually get even more complicated than that. So here's the same sort of diagram, but in this case, it kind of reflects what the actual frequencies are within little buckets. This is called a frequency histogram. And as you see here, it's not only the case that we have a little bit of skew probably to the left. We're pulling the whole thing a little bit to the left, but you actually have not a nice homogeneous peak. You've got a bimodal distribution here. And that sort of thing can cause real havoc with our choices about statistical testing. So imagine, for example, that then I tried to draw or assume a distribution to this. It might have this sort of central point on it. The mean and median might be somewhere close to the middle there. It would have a mode that was off to the right. But it wouldn't, that black curve doesn't really reflect at all what is going on in the underlying data. And so the answer to that question was that A, B, and C are the mode, the median, and then the mean is pulled further out. And we'll come to the potential, once we do this question, we'll come to the potential error that that we want to avoid in thinking about distributions. Okay, so question 3 is that a 3-year-old child scores 2 standard deviations below the mean on a standardized developmental test. That child is more delayed than what percentage of the population? 68, 95, 97.7, 99.9. Okay, so we have that about half said 95% and 30% said 97.7%. Okay, so the second way of describing that statistic is, or sorry, that distribution is not just where the middle of it is, but rather how wide it is. And that's something that's called dispersion. I actually have the plot for dispersion got moved to the next question, but you can see on here, this box plot is basically one of those frequency diagrams just turned sideways, right? So here you have the median. Here you have something called the interquartile range, and then you have various descriptions of how far out the outliers are. Are they here similar to this or within this so-called inner fence? Are they outside of the inner fence and within and so-called outer fence? So by looking at this, you can see that we're not only interested in what the median is, but rather at what the spread is, or the dispersion. Now, that spread is very relevant. And putting it together with the central tendency is very relevant, because a lot of what we're going to try to do is to map our data onto particular distributions that we know something about, so that we can answer the question that you just saw. As you all probably remember, one of those curves that we can employ for that purpose is something called the normal curve. And it is just a frequency distribution that has particular characteristics. First, the mean, median, and mode have all the same value. And you'll remember from our question that what that basically means is that it's a symmetrical distribution. It's symmetric about 0, so it's kind of normalized to 0. And the standard deviation of that curve, which we'll talk about in a bit, is 1. Why does that matter? Well, statistical tests often assume that data came from that curve. There are some little statistical quirks, like that the mean and variance don't depend on each other. And importantly, some, but not all, natural phenomena are actually normally distributed. Now, if we plot values on a normal curve, the spread of that curve, the dispersion, is measured in standard deviations, 1, 2, 3, 1, 2, 3. And because of the fact that it's centered on the mean, and the mean is 0, and that the standard deviation is 1, you can also determine the percentage of values that are within the mean and 1 standard deviation, within the mean and 2 standard deviations, and so on that curve. So in our case, the answer to that question is that this baby was 2 standard deviations below the curve, which is normal on tests like the one that we were kind of alluding to. And so we were asking, what is the percentage of patients who have developmental scores that are above that? And the answer isn't actually 95%, it's actually 97.7%. Now, for the purposes of training courses, I have this little brain up here that we use, and that's basically just to remember to memorize this. And if you do, you'll always be able to determine what the percentages are. So, doctors Brumberg and Nair would be in the top 0.1% with developmental and IQ scores at 3 standard deviations above the mean, for example, whereas I might be over there. So, so to answer this question, an infant scores 2 standard deviations below the mean on a test, more delayed than what percentage of the population? And the correct answer is actually 97.7%. Okay, so what is the first error that we can make? The first error, and it really is fundamental, even in really complex statistical analytic plans, even in randomized trials, one of the first things that solid statisticians will do for us is to print out the distribution of the data and allow us to look at it. So the first thing that you're going to want to do is to plot your data and then to describe your data using the mean and standard deviation. Okay, so now that we can plot, describe distributions of samples, now we have to start thinking about what we can do with that information. So in question 4, we ask this: a study has 90% power to detect a doubling of mortality in infants who are placed on this new ventilator at an alpha level of 0.05. What is the chance that the study will fail to detect a difference in mortality if a difference in mortality does in fact exist? Oh, second in that one. Okay, so we have about half saying 0.1 and about half saying 0.05, as you see here. Okay, let's talk now about why it was that we were interested in determining the distributions, the shape of distributions. In so-called inferential statistics, so now we're getting beyond just describing things, but we want to try to use a sample, which is basically whatever it was that you were studying in your analysis, in your study, to estimate what is happening in the population. So we go from sample to population, right? And that is based on a number of things. You can imagine that if your sample was only three patients, then estimating the 4 million births per year in the United States might be difficult. Whereas if you have a sample of 100,000 patients in an environmental study, you might be able to do a better job at that estimate. So there's a lot that goes into going from sample to population. And basically that a lot is divided into 2 steps. The first is that we describe the relationship between the sample and the population by some sort of statistical distribution. And that distribution, which might be something like the normal curve we looked at, a T curve a distribution, a chi-squared distribution, that distribution depends on the characteristics of the data as we've described. In step 2, then, we can use powerful means to compare those underlying distributions in the population. So you are involved in collecting data about a sample, and statistics is non-descriptive. Inferential statistics is involved in taking that, mapping it onto a population and comparing this, the population. So this is kind of what it looks like. We have here's sample A. You've collected actual data on those 7 patients, and here's sample B, and you've got 6 patients here. And you determine based on the mean and standard deviation that can be mapped onto a curve that looks like this, and that this can be mapped onto a curve that looks like this. Now, what we wanted to do was to say, well, does sample A and population A, who maybe were exposed to some environmental risk factor, do they have a different outcome to sample B and population B? Are the means for these populations actually different? The key issue, of course, is that as we're comparing those means, there's overlap between almost every two curves that we can pull up that are measuring the same thing, and we have to have a way of describing and measuring that overlap. The question that you just heard is basically a way of describing overlap between 2 or more curves. So in order to create a structure for this, you create a test hypothesis, and most of the time that test hypothesis is the null, right? We say there's no difference between the 2 groups, because as a structure, we are used to kind of knowing how the degree of overlap is then described. And then we determine 2 errors that might be involved in that overlap. The first is a type 1 or alpha error, in which we reject that hypothesis if it's true, right? We conclude that there's a difference between those 2 curves even when there is not. So we're basically kind of assuming that there's not enough overlap between those. The statisticians don't like it when we use these words, but in order to remember, I use this term false positive. An alpha error is basically concluding there's a difference when there's not. So it's kind of like a false positive. A type 2 error or a beta error is kind of the converse, right? You accept the null hypothesis even when it's false. So you say there's no difference, but in fact there is. So that is analogous to a false negative. Now, power is kind of the positive flip side of a type 2 error. In fact, it's 1 minus the type 2 error. And it's the probability of rejecting the null hypothesis when the null hypothesis is false. So the probability of detecting a difference if it exists. And so we're used to hearing about power calculations. Essentially, a power calculation is a way of determining what sample you need to avoid a type 2 error. So again, this is a memory slide. Know what a null is, alpha and beta errors, and then the power is 1 minus the beta. Okay, so here a study has 90% power to detect a doubling. If you're on this new ventilator, what's the chance that you'll fail to detect a difference in mortality if in fact it exists? And the answer is 0.1, because it's essentially 1 minus the power. We'll come to the alpha level in just a second. So error number 2, and this is also ubiquitous across all sorts of types of tests, is interpreting studies that have non-significant results and have low statistical power as negative, when in fact they're inconclusive. So that overlap basically means that we haven't, there's some degree to which we can't exclude the possibility of a positive effect, even when we seem to have a non-significant result. So how do we fix this particular error? Well, the first thing to do, and trialists do this universally. I think some of us in other areas of research don't necessarily, because we're using whatever data we have available. But ideally, you want to first of all choose a desired power prior to undertaking the study and try to figure out how you can get a data set that has that amount of power. And based on that power, so 90% is a good power, 80% is still a good power, there's a 0.2 chance of making a type 2 error. Based on that power, you can calculate the resulting standard sample size rather. So you take the power, you take the means and standard deviations of the two groups, and you can say, well, I need to find, either run a trial that has this sort of sample size, or I need to find a data set that has this many patients in it in order to be sure that I'm not rejecting a true effect of exposure on outcome. Where do you get the means and standard deviations, since you haven't done your study yet? You get them from similar groups. So for example, if you wanted to know, if you're studying a new drug, for example, you might know that the incidence of bronchopulmonary dysplasia in the same population of patients is 32% and has a standard error or standard deviation of say 8 or 10%. And then you can say, well, I want to reduce that by 25% with my drug, or I'm going to assume that I'm going to reduce it by 25% with my drug. And now you have the standard deviation of the two groups, you have a mean of the two groups, and you can put this into an online calculator that is easily Googleable, or better yet, partner with a statistician. She will know what you're talking about because you actually have this lexicon now, and will perform a series of power calculations telling you what your options are. So that's error 2. Okay, so the next question is sort of on the same topic of overlap. A study determines that women MDs practicing in academic pediatric settings have salaries that average 18% less than their male colleagues, with an adjusted p-value of 0.04. Which of the following is true? The probability that that's a fluke is 4%. There is a 96% probability that this is due to chance alone. The proportion of women earning less than their male counterparts is 96%, or none of the above. Watch that. Cool. Great. So 80% of you said the probability that this is a fluke is 4%. So let's go through and talk a little bit about, oh, actually there's one more here. So this one is that a large randomized controlled trial recently showed that administration of RSV monoclonal antibody to healthy late preterm and term infants resulted in a 75% reduction in medically attended RSV, in pneumonia or bronchiolitis. Adverse consequences were similar in the two groups, but the PI would like to ensure that the intervention is safe across all populations. So she asked that you confirm that there are no differences in 5 different adverse events at each of several weeks of gestation, at each of 4 weeks of gestation, 35, 36, 37, 40, and greater than 40. So which of the following is true? First, that there's no concern for multiple comparisons because the question was part of the analytic plan for the trial. Second, on average, that analysis will falsely reject the null hypothesis at least once. You should set the p-value at 0.0025 to be careful, or 0.2 and 3, or numbers 2 and 3. Okay. So we have a pretty even distribution of rejecting the null hypothesis at least once, and that and the p-value of 0.0025. Okay, so let's talk about p-values, which are somewhat related to this overlap that we've been talking about. The p-value, I'll say going into this, is something that was not terribly controversial around amongst clinical investigators, non-math people, until relatively recently, until really the last 5 or 7 years. And there's been an increasing penetration of concern about p-values from the statistical world into our world since then. So the definition of the p-value that you will read in books, and that I think is still worth committing to memory, is that it is the probability that a random sampling of 2 identical populations would lead to a difference at least as large as those observed in this experiment, in a particular study. The other thing is, or another way of thinking about this is that it is analogous to the type 1 or alpha error. It's kind of the false positive. It's a false positive concept. It's the idea that you might accept an alternative hypothesis when in fact there is no difference. So what are the problems with it? Well, what we tend to do, right, and we do this almost universally in thinking about randomized trials. I do this. This is one of the things I have to keep revisiting when I come back to teaching about this. We have a great study. It's really well done, a great randomized trial. It's big and well powered and perfectly executed. It shows a non-statistically significant result. And then we say, okay, well, that means the null is true. It means this drug doesn't work. And in fact, the p-value is not the probability of the null being true. Okay, it's just a probability that you might see a difference at least this large, as least as large as those observed in this experiment. It also importantly doesn't measure the size of an effect, meaning that smaller p-values don't necessarily mean the effect is more prominent. And that's something else that we do all the time, right? You've probably been in lectures where somebody says, well, I mean, the p-value is 0.001. This is a really important, this is a big effect. But it doesn't actually measure the size of an effect. It just measures how incompatible your experiment was with the idea, with the null hypothesis. So what the reflex to being concerned about p-values has been, well, we should talk about confidence bounds instead, in our kind of less informed world. Remember, this is a non-statistician's talk about statistics, right? So the confidence bound also does have problems, though. So what is the confidence interval? Well, the confidence interval is just defined as this: based on the sample's standard deviation and its size, and when you put those two together, it's something called a standard error. We are 95% confident that the limits of the confidence interval cover the true value of a population mean. Okay, so you go from your sample where you derive a confidence interval, and you say there's a 95% chance that covers what the true mean is in the population. Or, and I always like this one, if we drew samples of the same size 100 times, 95% of those of the confidence intervals would include the true population mean. So that's probably the easiest one to remember, because you can say, well, if I did this randomized trial 100 times, 95 times the confidence interval would cover what the real population mean is. Or here's another one that they use on toothpaste commercials: results accurate to within plus or minus 2 SD 950 times out of 1,000. Okay, but as I said, you can still get that wrong, right? So the following do not describe confidence bounds. 95% of the values in the population are within the upper and lower confidence interval. Remember that this is the population is a distribution of sample means, not in individuals. Okay, so it isn't that 95% of the values in the population are within there. It's just that it will cover the true mean 95% of the time. Or similarly, the true value is within A and B 95% of the time. The true value of the population never changes. It's just that our estimation of the confidence intervals changes based on the sample. Okay, so probably of those two, just remember the second bullet point here, and you'll get confidence interval right. Okay, so here was our question, and there are actually two answers to this question. If you're asked, if for those of you who are going into your board exams, if you are asked for the Stats 101 answer to this, it's basically number one. It's the idea that you falsely rejected based on, or that you would see a result at least as large as this based on chance alone. And I kind of translated that to fluke of 4%. But in fact, it is, as we've heard, a lot more nuanced than that. And it also includes, it's not just based on chance alone, it's based on all of the assumptions that went into setting up the study and setting up the statistical test. So the Stats 301 is that it's not just that the result is a fluke. It is, we go back to that issue of seeing at least this large a difference based on chance. Okay, and then the next one was here, and I think most of you answered 2 or 4, and in fact, this answer is both of the above. See where, yeah. So we know that that there is a 5% chance that you will falsely reject the null hypothesis at a p-value of 0.05. So if you perform 20 comparisons and you do that over and over again, eventually you can be expected to falsely reject the null hypothesis on at least one of those 20 comparisons, which basically translates to your saying, aha, 37 or 35 weekers have an increased incidence of adverse consequences, right? So you will take one of those 5 times 4 cells or categories, you will do a statistical test on it along with 19 other ones, and one of them will potentially come back positive. So this is a cautionary tale for repeated tests. So what can you do to get around that? Supposing you say, well, you know, the very nature of this is that I have to try to figure out these subgroups with certain caveats. What you can do is to take a p-value threshold that you would normally use and divide it up by the number of comparisons, for example. So if you would use 0.05, you can divide it by 20, and you could set the p-value for your consideration of so-called statistical significance at 0.0025. That's something called a Bonferroni correction. There are various other versions of that, but importantly, you do want to be stricter as you go into thinking about making lots of comparisons. Okay, so what is error number 3? Having thought about overlap and about p-values and confidence bounds, error number 3 is reporting only p-values. I think it's in most, although there are some journals that have banned them apparently, in most cases you will need to report hypothesis testing and p-values, but you can report them along with confidence bounds, which gives you some additional feeling for the size of the effect. You can provide a correct interpretation of the p-value in the discussion as we described. Now this article, Greenland et al., I would really suggest all of you just look this up. It is really an excellent article. And at the end, it goes through 8 or 9 different statements about the p-value, talks about why they might be problematic and why you shouldn't say that. And you'll have to read it a couple of times, but it's made for us clinicians, and it will really help you to understand this issue of p-values. And then the third fix is to rely, as you're talking about confidence bound, say you're talking about a randomized trial, you can rely on this idea that the results could be as high as this or as low as that 95% of the time. They'll cover the population mean. And I've kind of gotten into the habit of starting to say that about trials as well. Okay, what's error number 4? Well, that's the second question: undertaking multiple post hoc and subgroup comparisons without considering the consequences, that you might falsely reject the null hypothesis for some of those. So how do you get around that? Well, you can specify those comparisons in advance, and ideally, and this is what happens in some kind of big formal studies, you consider power when you're undertaking those subgroup comparisons, so that you can be basically treating them similarly to whatever the primary comparison is. And then, as we discussed, you can use a more conservative p-value threshold, something analogous to the Bonferroni correction. What I'm in selecting that particular issue, the Bonferroni, what I'm trying to do, as I said earlier on, was to give you a bit of a lexicon to talk to your statistician about certain issues. So if you were to say, listen, I need to, in response to that question, for example, I need to make these comparisons, and you can talk to a statistical or quantitative colleague and say, I'm thinking about using a Bonferroni correction. Probably what they'll say is, no, what I would use is this one, but they'll know exactly what it is that you're talking about. So think just having that lexicon of introductory concepts is going to be very useful to you. Okay. Question 7. So now we have this idea that we're going from sample to population. We can describe the sample using mean and standard deviation and other things. We can we know that what we're going to end up trying to do in certain types of statistical tests is to compare 2 distributions. And now we're going to talk about what those statistical tests are. And just as I just described for the correction, I'm going to ask, or I'm going to give you 3 tests to remember here, 3 only. They're on this slide, and they will basically be a starting point because each of them has a little pathway beyond it of tweaks. Okay, so first question: which test would you propose initially in your analytic plan to compare weight gain in grams in infants who received human milk fortifier to those who did not? The second question: which test would you propose initially in an analytic plan to compare the occurrence of at least 1 hospital admission over 1 year between children with mild asthma and those without? And the third question is, you're interested in understanding whether postmenstrual age at which positive blood cultures are observed in a population of infants in the NICU differs by term versus preterm. So in each of those cases, just try to think about which test you would use. So the first one, weight gain in grams based on human milk fortifier. Second one, admitted or not, based on asthma. And the third is timing of positive blood cultures in terms and preterms. Okay. So for the first question about 2/3 to 3/4 of you said t-test. For the second one, 2/3 said chi-square test, and for the third one, half said Mann-Whitney, and the rest were just distributed amongst the other two tests. Okay, so as we're thinking about the statistical test, we're going to again look at different dimensions of the data. So and the sample. The first is what type of data are we dealing with? Is it categorical data? Is it continuous? And I've lumped continuous and integer in here because they tend to overlap. What is the distribution of the sample? And here, this bullet has to do with moving from the sample to the population. So if you can infer a distribution from the sample and come up with something like a normal distribution or a t-distribution in the population, then you can use a set of tests that are called parametric tests. If the distribution is weird and can't be mapped onto something that is that we know about, so we saw that bimodal distribution at the beginning, for example, then we use a set of tests that are called non-parametric tests. So far we have type of data, we have whether we're going to use parametric tests, known distributions, or non-parametric tests. And then the type of comparison desired. And so this is whether we are matching, whether we're doing the same measurement in the same patients on a repeated way, for example. So are we doing before and after in the same individual, or are they completely separate individuals? And then the final aspect of the test is how many comparisons, how many variables do we want to compare on? Is it just got the drug, didn't get the drug? Is it got two doses of two levels of the exposure and one placebo? The number of comparisons that are desired. Okay, so first of all, let's just think about parametric tests for continuous data. And I'm going to give you just one of those, which 2/3 of you already had. And that is the so-called t-test. We can divide that t-test up into whether it is a repeated test in the same population, so-called paired t-test, or whether it's in two separate groups, a so-called unpaired t-test. And there are ways of going beyond that and comparing many groups, for example, many variables. So again, remember, we're going to go from sample to population in this case, and in this, just to sort of fill out what we said at the beginning. In this case, for a t-test, basically what you're saying is that the sample can be mapped onto or described using in the population using a so-called t-distribution, which is basically just a normal distribution with thicker tails. Okay, and similarly, sample B onto another t-distribution with thick tails. Okay. So then the second class that we're going to think about is for categorical data. Here you're comparing two separate groups, and you're going of categorical data, and you're going to use a so-called chi-squared distribution. Now, how does that work? Well, when you think about designing a chi-squared analysis, you're going to default to this 2x2 table. At the top, we're going to have the outcome, and at the left here in the rows, we're going to have the exposure. And each of these has a different circumstance: asthma admitted, asthma not admitted, no asthma admitted, no asthma not admitted. And basically, the chi-square test just determines if the counts in the cells differ from what is expected based on chance alone. Now, what happens if, look at the chat here. What happens though if we have something unusual about the data that prevents us from mapping? In that case, then we use so-called non-parametric tests. And the one I'm going to ask you to remember, is the so-called Wilcoxon rank sum test. Or if you're doing a before and after, two paired groups, you can use something called the signed rank test. So the first two bullets there. And basically that works like this. Remember, the concept here was that we had a term and preterm, and we wanted to see what day of life or postmenstrual age you had an onset. I guess it was day of life. You had an onset of bacteremia. Now, the thing that you had to appreciate to answer that question is that there's early onset sepsis and late onset sepsis, right? So this is probably something that has two peaks, two modes. And so it's a so-called bimodal distribution. And in that case, you're not gonna be able to map it onto a T distribution or a normal. Instead, you're gonna use something called a non-parametric. To make it concrete how that works, you just write out all your data with the day of life that the culture came back positive, and then you rank those days of life with whatever the variable was sorting it out, preterm versus term. You just add up the ranks, 1 plus 3 plus 5 plus 7 plus 9, and basically look up that ranking, that sum of the ranks, and the tables will basically tell you what the probability is that those two those two samples are taken from a different population. It ignores as you can imagine, because you're just looking at ranks, it ignores a smooth line, and so you can use it in different situations. So which test would you propose initially in your plan for weight gain based on human milk fortifier, t-test as we described? Just a little thing to remind you of, or so that you'll remember a t-test. What does the t-test have to do with not tea but beer? Well, it turns out that this was actually developed by a guy named William Gossett, who worked for Guinness breweries. And at the time, Guinness breweries had been hiring, they wanted to kind of scale up operations, and they figured they were going to need some really smart people in order to do that. And so they started hiring people out of prominent universities in the UK, like Cambridge and Oxford. One of the people they hired was this William Gossett, and he was charged with moving into the future the way that they assessed the hops that went into their beer. So rather than just tasting batches, which you couldn't do as you got bigger and bigger, he came up with a test to look at the percentage of resin in two types of in batches of hops, so that they could standardize what went into their beer. Now it worked. He developed the t-test in order to do that. And in order to, he wanted, because he was of an academic bent, he wanted to spread this around. The proprietors of the company didn't really want him to do that, and so he published under the name Student and the pseudonym. So that's why this is called the Student's t-test, and it has a history in beer. So what would you propose for the occurrence of at least one hospital admission? So yes or no between children who had a history of mild asthma or those without. Chi-square test as we described, and then we went into detail about this idea that on a bimodal distribution, you would probably use something like the Wilcoxon rank sum, which is also known as the Mann-Whitney. Okay, so the fifth error that we can add to our list is to use parametric tests when the data don't match a known distribution, or you could choose the wrong parametric test. You just hit send on a t-test versus something else. So how do you do this? Well, we're going to come back to the beginning, which is plot your data. Take these three tests and just read up on the basic assumptions. There are other assumptions that I haven't gone into today, but you don't have to learn the assumptions, mathematically necessarily, and you don't have to learn them for every test. Just try to get them for these three. You can, when you're thinking about parametric versus non-parametric, you can actually apply tests to the data to see whether they meet the assumptions of being able to map onto a particular distribution. And then, as I said, once you've said, once you've decided, well, it seems like this should be a t-test, just ask your quantitative or statistical colleagues to help you to tweak your selections, and I know that they'll be happy to do that. The next error is assuming that samples are independent when in fact they're dependent. So most of these tests will assume fundamentally that the two samples are completely different. And if they are drawn from the same individuals, then the amount of variance is actually reduced. And so the results that you get will be inaccurate, essentially. So the way to address that is partly not statistically, just to ask, are these samples completely different from each other? So are they in a different, different groups of babies? Are they different hospitals? And then you basically use that information to choose either repeated measures or an independent test. And then error 7 is just drinking Guinness beer because it's gross. Okay, so now question 10. So you are interested in exploring whether the administration of packed red blood cell transfusion to preterm infants is associated with the development of necrotizing enterocolitis in the ensuing 48 hours. This is an example of, you're aware of literature that suggests that anemia might be a cause of NEC. So this idea of thinking about transfusion and anemia and NEC is an example of which of the following phenomena. So is it bias, effect modification, confounding, or both 2 and 3? Okay. So about a 2/3 of folks said it was effect modification, and and 1/3 said that it was confounding. Okay. So what is confounding? We use this in kind of a generic lay way of meaning, but there's actually a very specific definition to confounding. It's a distortion in the measure of association, which is exposure to outcome, in which the primary exposure is that measure is affected by some other factor that's also associated with the outcome. And that some other factor could be a risk factor, it could be a prevention factor, negative family history. It could be a surrogate for a whole bunch of other types of factors like socioeconomic status. It's just something that distorts the association. Now, how does that work? Well, the technical definition of a confounder is that it has to be associated with both the risk factor of interest and with the outcome. So both the exposure, the confounder has to affect the exposure, and the confounder has to affect the outcome. Importantly, the confounder has to be unequally distributed between the groups being compared. If it's equally distributed, you'll probably never know because it will kind of balance out, and the effect will be based on something else. And it has to not be on the causal pathway between exposure and outcome. Okay, so you don't want to go through the confounder. The confounder is separate and affects both ends. Okay. How do how do you detect that in practice? Well, the main statistical way, although you can start to think about it non-quantitatively, the main statistical way of doing this is to compare whatever association measure you're using before and after adjusting for this potential confounding variable. And if that measure changes, say it's a relative risk, if it changes, and people will sometimes say more than 10%, then you can say, well, that this is a relevant confounder. Now, how do you get rid of it if you see that you have something that's affecting both sides and it's distorting your result? Well, you can fix this either when you're designing a study or when you're analyzing. If you're designing a study, one thing you can do is restriction. You can basically just say, I'm only going to look at a certain level of the confounding variable. So for example, supposing sex was a confounder for some particular outcome, you could just examine your issue in males. And in that case, there wouldn't be any issue of confounding. You can match the two groups on the confounder, or you can randomize. And randomization basically addresses the second criteria of the three criteria, right? If you randomize with a large enough sample size and everything is distributed based on a flip of the coin, then the incidence of all confounding factors should be equal in the intervention group and the control group. Okay, so randomization is basically a means of ensuring that factor 2 of a confounder is criteria 2 is not in play. Then out of the way. Then during an analysis, you can either stratify, meaning that you'll report out for each level of the confounder, or you can perform multiple regression, and we're actually going to talk more about that in a little bit. Okay, so now let's talk about effect modification, because that was another one of the options. So with effect modification, the magnitude of the measure depends on the level of a third variable. So this isn't so much that you have a third variable that's affecting the exposure and affecting the outcome and screwing things up. It's that the actual effect differs according to different levels of the effect modifier. And you can imagine that in that situation, reporting one overall estimate of association might be actually misleading. So what we do instead is to stratify the analysis of exposure on outcome by different levels of the variable, or we can use interaction terms in multiple regression. Here it is diagrammatically. So we have, first of all, exposure to outcome that goes along some sort of causal pathway. And the confounder will affect the exposure, and it will also affect the outcome. In contrast, here we again have exposure to outcome along a causal pathway, but also along that pathway, an effect modifier at one level will cause a higher level of the outcome, and an effect modifier at another level will cause a lower level of the outcome. So this might be, for example, the gestational age effect on incidence of neck. So to answer this question on anemia, neck, and packed red blood cell transfusion, it's probably best described as a confounder in the sense that anemia affects outcome, anemia affects whether you have a packed red cell blood transfusion, but anemia may or may not be on the causal pathway packed red blood cell rather. I'm sorry. So anemia in this situation might be an effect modifier, whereas packed red blood cells could actually be a confounder. Okay, so now we mentioned linear regression. Let's go on and ask a question specifically about that. So a linear regression model. A linear regression model includes birth weight as the dependent variable, and it includes the independent variables: gestational age, glucose load test, the fasting glucose level, and a maternal, or sorry, glucose load test, glucose level, and a maternal birth weight. And you hear that the model has an overall significance of less than p less than 0.0001, and an adjusted R² value of 0.795. When you add in the paternal birth weight to those three variables, the adjusted R² decreases to 0.763. So in interpreting this linear regression, which is true, the new variable explains 76% of the variance in birth weight. The probability that the new variable is associated with birth weight is 76%. The probability that the association of the new variable with birth weight is due to chance alone is 0.0001. Or the new variable explains less of the variance than would be expected by chance alone. Okay. So again, a distribution. About half of you said that in interpreting regression, the new variable explains less of the variance than would be expected by chance alone, and the rest are distributed amongst the other results. Okay. So how do we do regression? And you know, I gave you t-test, chi-square test, a non-parametric, the rank sum test. We probably, if you look at our literature, linear regression or multiple regression is probably I would say up in the most amongst the most common sorts of tests. So it's useful to go back and think about what it is that it's actually showing you. So how do you do a regression, or how does the machine do a regression? The first thing is that you're going to make a scatter plot of your data. Remember, we're always going to plot our data somehow. And in this case, because we're trying to determine the association of two variables, rather than just looking at a distribution, which we were looking at earlier on, a frequency distribution, we're going to plot two variables against each other. And so here we have gestational age on the x-axis, and we have birth weight on the y-axis. Each of these dots is referred to as a y sub I here. The second thing you're going to that we do, or that the machine does, is to plot the mean of all of those values with respect to the outcome variable. And so that's this mean line the y bar line that you see in the middle. Okay. The third thing you're going to do is to try to draw a line through that fits those dots. And just as with any line, y equals mx plus b, right, from high school, this line, if it's a linear regression, has that sort of a format: y equals alpha, which is the intercept, plus mx or beta x, and then there's an error term stuck onto the end of it. Okay, so that's fair enough. But how do we know that that line is the right, is the best line? Well, we now start to determine how far the dots are from any particular line that we can plot, and we do that in the same way that we calculated standard deviation, which at the beginning of this, which is that you take the distance from each dot to the line, and you square it. The reason you square that distance is that if the line goes through the middle, it would the so-called sum of squares would end up being 0, because some would be positive and some would be negative, and that's not the concept that you want. You want to determine how far away things are. So you square the distance in each case between the dot and the line, and then you add all that up. That's the so-called regression sum of squares, or explained sum of squares. And then you basically adjust the line until that value is minimized. We see the equation for the sum of squares there in the box. Okay, so now you have the line that fits best through this group, and by minimizing the distance collectively of all those dots from whatever line that you've drawn. Okay, now we can try to determine how much of the total variation is explained, and the total variation is actually the distance of each of those dots from the mean squared, okay, and summing them all up. So in this case, rather than going from dot to line, we go from dot to mean, and we do that for all of the dots, add them all up, and that's the total sum of squares. Okay, so the R squared, which was asked about in that question, is basically just taking the area that is explained from here to here, adding up all of the areas that are explained, or sorry, all the errors that are explained, and dividing it by the total sum of squares, the distance between each of those and the mean. That's the R squared, okay, explained divided by total sum of squares. The adjusted R squared is basically a version of that just includes the number of variables in your equation, because you can actually take this only involved 2 variables, but you can actually take this and add another variable and put it into 3 dimensions, and add another variable and put it into more dimensions, and so it starts to get mathematically very complicated and difficult for us to conceptualize, but it's basically exactly the same thing. You're taking the distance of each dot from a line divided by the distance of each dot, the square of the distance of each dot from the mean, and that tells you how much of the total variance in the sample is explained by this line that goes through the middle of the sample. That's regression. So as I said, you can add more variables just in more dimensions, and basically, you know, the equation for that line is this one here, and it has various components to it. This is the alpha is where it intercepts the axis, the y-axis. We talked about this error, which is a different kind of sum of squares that we can get into at some point if you like. But the interpretation here of the core term is this: for every point increase in x, the outcome variable increases by beta, right? And if you blow it up into more variables, you're basically saying the same thing, but saying after accounting for all the other variables in the equation, for every point increase in x, y increases by beta. Now we have a way of dealing with other variables, of dealing with confounding specifically. And that's, you know, really the power of regression. But you have to know how it's developed, otherwise you're going to make mistakes. Okay, so this is the output that you get that'll be relevant to that question. If you run something in SAS, the first half part of this is the at the model level, at the whole, the global aspect of the model, and what we see is that it actually lists what the sum of squares is. Remember, that's the difference between each dot and the mean. It lists a so-called F statistic, which is basically taking the regression sum of squares, dividing by the error, which is the rest of the distance down to the rest of the distance down to the mean. You calculate this F, and then you get a p-value for that, and that p-value is basically the p-value that corresponds to whether the model as a whole explains the relationship between or whether there's a relationship between the two variables that you're considering, or between the variables that you're considering. So the R squared we looked at is also listed on here. It is the percentage of the total variance, remember, that is explained by the model, and the adjusted R squared takes into account how many variables there are. The second part of the output now goes into those parameters, into those beta X terms that we looked at. And here you see all of the different betas listed under the heading estimate. And for each of those, there's also a p-value that basically is from this is closely related to a t-test. So each of those has a p-value as to its statistical significance in predicting in association with the y. Okay. So now if we go back to question 11, we can say that it isn't that the new variable explains 76%, because that adjusted R squared is for the whole model. It's the percentage of variance that's explained by the whole model. It isn't that the new variable is associated with birth weight at a 76% probability, because this 70.76 has to do with the R squared. It has the 0.0001 here is the overall significance, not the significance for a particular variable. Instead, what we see here is that the adjusted R squared actually went down. Now, if you think about it, when you're adding in additional variables, you should either explain the same amount of the variance, or you should be able to explain more of the variance. It shouldn't go backwards. But if you divide by the number, in some way, by the number of variables in your model, and those variables actually aren't helping to explain anything, then the adjusted R squared starts to go down. So the answer here is that when you see the adjusted R squared not going up, it means that whatever variable you just added explains less of the variance than you'd expect by chance alone. Okay, so now we know about confounding, effect modification, and how to potentially address those with regression. So the next error is a failure to consider confounding and effect modification in your study design analysis. How do you fix it? You think about the possibilities based on theory and literature before you start. And this is actually really, really important. People have almost always looked at multiple exposures on the outcome and in the literature, and you should be able to pull out candidates. After you start, you can look for confounding by adjusting and not adjusting, and see if you get a difference in the association variable, a difference in the beta, for example, in that regression analysis. You can fix confounding, as we talked about, through a number of means, including multiple regression. And then you can look for effect modification by stratifying the exposures and the outcomes and seeing whether they're different at different levels of the variable. Okay. The next error has to do with the number of variables, which we kind of touched on in regression. Either you can omit variables, in which case you're going to kind of reduce the predictive ability of the model and potentially also leave out confounders that should be taken care of. You can include too many variables, as we saw in that last example, that including the paternal birth weight actually caused the adjusted R-squared to go down. It didn't have any effect on improving the predictive ability of the model. If you put in too many variables, what also tends to happen is that your model, your regression will be so particularly fit to the idiosyncrasies of your sample that when you try to take it out of the sample, it won't be predictive anymore. Okay, so that's called overfitting, and it's important to recognize it. It's important to think about it with, as I mentioned, with the adjusted R-squared. Or if you include variables that are collinear, meaning they all run together, it might reduce the ability to detect significant effects. How do we fix this? Well, first of all, you have to understand the output from regression. It's pretty easy to click run on one of these analyses and to just pull out the p-value. But as you see, it's a lot more complicated than that. Not terribly complicated, but it's more nuanced. You really have to look at all the different parts. As you're deciding what to include in the model, you're going to include variables if they are statistically significant one at a time, or if they're theoretically essential. Supposing you know absolutely that something is a confounder, then that's something that should be included in the model, sometimes regardless of statistical significance. And then if you find that variables aren't playing a role, as we just described for paternal birth weight because of the adjusted R-squared or the p-value, then you pull them out, and you do this kind of iteratively. There are even automatic algorithms that can do that in statistical software. But when you do that iteratively, you'll come to a model that really balances being able to predict with not being overfit to your sample. Okay, so the next question has to do with effect sizes. So if you have a randomized controlled trial, 500 infants are in high flow nasal cannula, and another 500 are placed on CPAP. 50 of the infants in the high flow group and 100 in the CPAP group have nasal excoriation. So what is the relative risk reduction in this case? Okay, so there's a little bit of a pause, so I'll just skip forward to the next piece of it. And somebody, by the way, asked which one is the control group. I guess we can consider this a comparative effectiveness study, but the control group probably in our field is probably CPAP. So about 50% of you, or sorry, about 60% of you said calculated 50%, and about a third of you calculated 10%. So let us go through here. So basically, now that we've looked at how we do comparisons, when we talk about measures of effect, we're talking about the specific elements on which we're comparing in terms of intensity of an effect, as opposed to the operation of chance. And there are a few that we should talk about that are most operative either in randomized trials or in epidemiologic studies. So the first of these is the so-called relative risk reduction, and that is the risk of an adverse outcome in the experimental group is reduced by this proportion relative to controls. And I've tried to give you kind of what the lay interpretation of this jargon might be here. In the odds ratio is a closely related concept, as we'll see, which states that the odds of an adverse outcome in the experimental group are reduced by this proportion relative to controls, and we'll see what the distinction is in a second. The absolute risk reduction is that the risk of an adverse outcome is reduced by this absolute percentage in the population, and the number needed to treat is that you need to treat this many patients to avoid one adverse outcome. In thinking about these, this is a useful sort of schematic picture. We see in this picture that the control group has a rate of some outcome of 8%, and the treatment group has the rate of an outcome of about 4%. The relative risk reduction of between here and here is going to be 50%, right? This is half of this. But the absolute risk reduction here is going to be the difference between these two, 8 and 4, or 4%. So keep that in mind as you're calculating. A number of you were able to calculate this. I don't know if you were using equations that you had in your head, but I like to present a way of doing this that basically relies on first principles. So in order, whenever you get a question like this, or you have a study where you're trying to figure things out that involve dichotomous outcomes and dichotomous two groups, what you're going to try to do is to put the outcome again, as we did earlier on for the chi-squared. You put the outcome as columns and the intervention as controls. Now, it's customary to label those cells, as you see here, and then to generate equations that will allow you to calculate relative risk and so on. I actually prefer not to do that, and instead to calculate so-called event rates. So the control event rate is basically the probability of having the adverse outcome in the control group, and you can imagine that's C over everybody in the control group, C plus D. The experimental event rate is the same thing, the rate of the adverse outcome amongst everybody in the intervention group, A over A plus B. Now we can, using that information, which is really quite intuitive, we can then calculate these other measures, which might not be so intuitive. So the relative risk, relative just means ratio, right, is the experimental event rate divided by the control event rate, which you see here. We had calculated 50, or we'd showed 50 over everybody here, 500, and divided by the control event rate, 100 over 500. And so the relative risk here is 0.5, and the reduction in that risk based on being in high flow nasal cannula is going to be 50%. So you folks got that one right. Now, the absolute risk reduction is an important concept. So rather than being relative, the absolute risk reduction is just in the population, how many fewer individuals will have this adverse outcome based on being in group 1 versus group 2. And so you're going to take the control rate and subtract off the experimental event rate, 100 minus 50, and you're going to get 0.1. That's the absolute risk reductions tend to be important in epidemiology because you're trying to kind of think about the burden of illness in a population, the impact of changing some exposure in terms of not in relative terms, but in global terms of the population. So obviously you can see that this means that 10% fewer individuals would have nasal breakdown in the experimental group. Well, it also allows us to calculate the so-called number needed to treat, which is just taking that 10% and dividing it into 1. So you can imagine that if the number in the population decreases by 10% in absolute terms, then that's going to mean that you have to treat the whole population. You have to treat 10 individuals in order for one person not to have the adverse outcome, not to have nasal breakdown. The number needed to treat tends to be by far the most intuitive of these 3 measures of effect. And so it's really something that you should think about including as you do analyses, either the absolute risk reduction or the number needed to treat. Now, we also mentioned the odds ratio. So what is that exactly? Well, basically the odds are something that people use in gambling, and rather than being a probability, A over everybody, it's the likelihood of or the number of people who have an adverse outcome over the number who have a good outcome. It's win against lose. This horse has a 5-4 of coming in first, right? Win 5 times and lose 4 times kind of thing, instead of 5 over 9, which is a rate or probability. So the intervention odds here is A over B. We're going to do the same thing conceptually. The control odds is not C over both, but C over D. And the odds ratio is just the ratio of those two, analogous to the relative risk. So why would we ever do this? Why would we ever use the odds ratio? Well, probably the most important reason for it is that when you do another kind of regression that is closely related to what we just saw in linear regression, called logistic regression, odds ratios fall out directly from the betas, from the parameter estimates. So in trials and in epidemiology, where you have dichotomous outcomes as opposed to continuous outcomes, odds ratios are easier to pull out of the data. The odds ratio is related to the relative risk in a certain way. When the prevalence of the disease is very low, they're actually pretty similar to each other. And you can imagine why that would be the case, right? Because if the probability is very, very low, then the A to B will be pretty close to A over A plus B. But when the prevalence of disease is very high, the odds ratio won't be equal. And in fact, it will always overestimate the effect size, either up or down. So if the ratio is a reduction in the incidence of the adverse outcome, the odds ratio will be more dramatic a reduction. If it's an increase in the adverse outcome, the odds ratio will show a more dramatic increase when the prevalence of disease is high. So in a randomized trial, about half of you said 50%, which is correct. I think there was a hand raised.
Yes, there are also a few questions in the chat. I
Okay.
wasn't sure if you wanted to finish and then
I was going to go back to the questions at the end, if that seems reasonable. We're almost there.
Yeah.
Okay, good. Okay, so this error, the error number 10 is failing to distinguish absolute from relative effect of an exposure. And the key here is to calculate both absolute and relative measures. Importantly, the absolute measures will also depend on the incidence of disease in their own way. So if a control group is higher or lower in the population, then you could imagine that the number needed to treat is going to change, whereas the relative risk will not. And then error number 11 is not considering the effect of the exposure. So what we've just been talking about is specifically the largeness of the association between exposure and outcome. Okay, it's common to say, well, this was a statistically significant trial, or this exposure, the environmental exposure is there's a significant association, but importantly, that doesn't necessarily mean it's clinically relevant or clinically important, right? So effect sizes, although we tend to kind of discard them because they're relatively easy to calculate and to conceptualize, they're really central to what we do as medical people. Okay, one final question then, and then we'll do some questions from the audience. So you have 1,000 babies undergoing sepsis eval, 100 have an elevated immature to total neutrophil ratio, and 900 don't. Of those who have a left shift, 10 are found to have bacteremia. Of those who don't have a left shift, 15 have bacteremia. So this just asks you to calculate the sensitivity for an elevated neutrophil ratio for bacteremia. Okay, as the rest of you are kind of going through that process, we'll just skip forward so we have time for the last couple of questions. So this question was around test performance specifically, and there are going to be 4 specific dimensions of test performance that you're going to talk about: sensitivity, specificity, the positive predictive value, and the negative predictive value. And here you really also, again, want to be sure that you know what the lay description is. So the sensitivity portion of patients who have the disease that a test detects. The specificity is the proportion without the disease who are detected as negative by the test. So those are the true positive and true negative rate. And then there are 2 others that basically say, if you have a positive test, how likely are you to have the disease? And if you have a negative test, how likely are you not to have the disease? It's really important to distinguish the top two from the bottom two. And we'll see mathematically why that is the case, but they are very distinct elements. So once again, you're going to do a 2x2 table as you analyze your data. At the columns are basically whether a particular outcome like the disease is present or absent, and the rows are what you got on the test. So the outcomes always in columns in these formulations. And basically the sensitivity, we know that a positive test, the sensitivity is the proportion of people who have the disease who test positive. So as soon as you know the definition of sensitivity and have this 2x2 table, you can say, well, that's just this over all of these patients, which is this equation. So you don't have to memorize any A's and B's, you can figure it out from first principles. Now the positive predictive value is distinct. It's if I have the positive test, what's the likelihood that I have disease? And so it's this over all of these patients here, okay, the test positive. And because it doesn't just involve this column, but instead involves both of these columns, for that reason, the positive predictive value is associated with disease prevalence, okay? So you're gonna have more false positives as the prevalence of the disease goes down. Very important, because you can have really, really good tests that don't have very good characteristics if you apply them to millions and millions of people. Okay, so it will distinguish people who have the disease, but it doesn't mean that it doesn't have a false positive rate. So that for that reason, you want to report both sensitivity and positive predictive value. And then specificity is basically the same thing. You take all the people who don't have the disease, how many of them have a negative test result, and that's the specificity. Whereas the negative predictive value is starting with the test, how likely is it that I don't have the disease over here? Okay. So that's the calculation. I'm going to skip the ROC curve. But you can kind of take a look at that. So the answer here was 0.4, and now you know how to calculate that. So what is this last error that you can make? The first of all is confusing the positive and negative predictive value of something with sensitivity and specificity. And I saw this a lot during COVID, where newspaper reports would conflate these two issues. They'd say, oh, this test has this sensitivity, but then they would infer that if you have a positive test, that it was this likely that you had disease. And so it's important to calculate all of the above and distinguish them in words. Okay, well, that's the sort of run through. There, in addition to those 12 sets of potential errors that we can be on the lookout for, there are some overarching errors. The main one really is not planning the analysis in advance, or skipping directly to the analysis by just clicking run on your software. It's really easy to do that now. And then third, ignoring clinical importance. How do you deal with those? The first thing, and I really do this, is to write out a methods section, even if you're not applying for a grant. Just write out your methods section in a few paragraphs and create blank tables before you start. So commit yourself to a particular type of analysis before you get into things and just start testing and looking at stuff. The second really important bullet is to just plot whatever you can think of. Scatter plots, frequency histograms before the analysis. Look at them and just kind of think and let your mind alone to think about what the appropriate analysis might be. And then finally, to discuss the clinical importance, effect sizes, sensitivity, specificity, and so on, with equal priority to the statistical significance. So thank you. And let me go through some of these questions if folks have some time. I know that somebody had their hand up. Would you like to start with asking a question?
Yeah, let me, it's Dr. Praveen Chandrasekharan from Buffalo. Let me just
Hello, Praveen.
see. Yep, Praveen, you should be able to talk now.
Can you hear me, Jayshree?
Yes.
Hi. Oh, sorry.
Yeah. Hi, Dr. Spancic. I hope
Hi.
I got your last name right.
Yes.
It's always a pleasure to listen to your lecture again and again, and we learn a lot of things more. There are actually many questions that I have. So, but let me restrict it to a couple of them. One is, let's check with the probability. You just brought it up saying that the probability of 0.05, how overrated it is, and can you comment why is that? Why cannot be 0.06 or 0.07, and how does it affect the power?
When you say why is it not 0.06 or 0.07, can you explain that a little bit more?
So what if I mention that I want to keep my probability of my study, the chance that it's going to be significant at 6% or even 10% for the matter of fact?
Yeah. So I actually think that's a very good insight. The p-value of 0.05, it turns out is probably something that's kind of hardwired into us as human beings, that if, you know, I've done this experiment with people where I flip a coin, you know, and it says heads, and I flip it again, heads, flip it again, heads, and it keeps coming back heads. And when do people start to smell a rat? It's usually after about 6 or 7 flips, which corresponds more or less to a 5% probability of something being due to chance, right? And so it seems like that cutoff has that, but it's kind of like a 7-day, you know, it's like a 7-day antibiotic course. There's not a lot of other reasoning that it should be 5%. So you could say, well, we could make this a more rigorous cutoff in situations where I'm doing multiple comparisons, or maybe if it's something that I would rather adopt, even if the evidence is less, even if I have a higher chance of the data not being consistent with the null, right? It probably, in those situations, it would be reasonable to use a higher cutoff. I actually haven't seen that very often. The only place I've seen using a higher cutoff is in deciding which variables should enter into a regression analysis, where we'll often use like a 0.2 cutoff and say, well, that variable I will continue to consider it as something that should go into regression analysis, because later on I'm going to be looking for confounding and all that kind of stuff. But I haven't seen a journal article where we've said somebody uses a 0.07 cutoff, and it really isn't consistent. There's no statistical reason it should be 0.05. So I think your insight is correct. The practicalities of it are that I think it's still the case that if you went to a journal and said, you know, I'm using a p-value of 0.08 and I'm going to call that significant, I think they would probably not accept that just because it's been around for such a long time. But
I totally agree with you. Yeah.
You don't?
I totally agree with you on that.
Oh, okay. You're allowed not to.
So that leads to the next question, since you brought up the regression analysis and why we include factors that with a probability of 20%. So you had focus on your lecture on the regression line, and most of the regression models report, if it's a retrospective analysis, a gifted odds ratio. Mm-hmm. And then they never report a regression value to that. So how much of it should we focus on the regression value versus the adjusted odds ratio value?
Sorry to interrupt, but we are over time. So maybe Dr. Spancic can quickly answer this, and encourage, show your email. So for those folks who didn't get their questions answered, they could maybe email you their questions as a follow-up.
Absolutely. My email's on this slide, and I'm happy to correspond by email, or if it's more complicated, we can set up a time to chat for sure. I'm sorry for not leaving enough time for questions. And maybe, Praveen, that the answer to your question will take a little bit more time. Do you want to do that offline as well, then?
That'll be great. I mean,
Yeah. Okay.
Sure. I understand. It's a great lecture again. Thank you so much.
Okay. Thank you so much, everyone, for sticking through to the end.
Oh, that's fine, Dr. Zupančič. I actually feel bad for one of this, for the questions that were asked in the chat. Somebody had sent this question ahead of time, and maybe just address the first one, and then the rest of them we'll do soon after this, and then we'll close the session out in a couple of minutes.
Okay, this is from Dr. Jawale.
Yes, so yeah, propensity scoring.
Yep. So asks, can you please explain the value of using propensity scoring versus case control with a higher case match when the sample sizes are high? It seems like case-controlled study designs were fine, but there's been a shift towards using propensity scoring. So propensity scoring has caught on because it's a way of trying to essentially, I shouldn't say overfit, but to try to use a larger number of variables to determine whether a patient is in one class versus another, one group versus another group, and then almost to simulate a trial, because you've taken care of so many so many of the potential confounders using that approach. I think it's true that it's become kind of trendy, and it seems I still use case control, and we've done sort of matching as you described, and so I think it's probably just a little bit of advocacy on the part of folks who like to use propensity scoring. I don't think there's any reason that you should have to abandon your case control approach, Dr. Jawale. But I'm happy to talk to you about it in more detail if you like.
Thank you so much. And I actually, if you'll see, I put your email in the chat. Thank you so much for your willingness to share it with the many people who attended today. So with that, we'll conclude this wonderful session, again sponsored by ESPR and Reckitt Mead Johnson Nutrition. And Dr. Zupančič, again, thank you so much for this. I think I won't tell you how many of the questions I got wrong, but let's just say it was a significant amount, and it just tells me that I need to keep doing this.
I have to tell you, I was standing up in front of 400 people, and I got one wrong too, and I had written it. So
well, thank you again. And with that, I'd like to end the session. We have an exciting Shark Tank style session on encouraging diversity in researchers starting very soon, and we'd like to encourage everybody to join in. Thank you for attending, and have a very nice evening. Take care.
Thank you so much.
Thank you.
Bye.